the final of diffraction, we get the interference. This is the intensity distribution curve as like this. Suppose if we take a graph of intensity versus path difference. Intensity versus path difference. We'll get first at the center. We'll get central bright band. Okay. After the central bright band, the intensity is minimum. Again, it becomes maximum. Again, it becomes minimum. Again, it becomes maximum. Again, it becomes minimum. Like that. Again, it becomes maximum. Again, it becomes minimum. Okay. That means on either side of the central band, the intensity goes on minimum. Again, it becomes maximum. Intensity goes on minimum, again it goes maximum. It becomes minimum, it goes on maximum and minima like this. Okay, this central bright band is known as central maxima. Central bright band is known as central maxima or principal maxima. Okay, at this position, constructive interference takes place, so we will get bright band, so that is called as central maxima. At central maxima, intensity is maximum. Okay, after this central maxima, the intensity goes on decreases and reaches to 0, that means minimum. So this minimum point is called as minima. First minima, it is called as first minima. Okay. After this first minima, again intensity goes on, increases like this. Again it goes on, increases like this and reaches a maximum point, and this is known as first secondary maxima. First secondary maxima, because this is the first primary maxima. Therefore, it is called as first secondary maxima. After this first secondary maxima, the intensity goes on, decreases and reaches to 0. That means minimum. It is known as second minima. Okay. Again, after the second minima, the intensity goes on, increases and reaches at a maximum point, and this is called as second secondary maxima. Second secondary maxima. Again, after the second secondary maxima, intensity goes on, decreases and reaches a minimum point, and this is known as third minima, like this. In interference pattern, the intensity is maximum at the center, and that is known as central maximum. After this maximum intensity, intensity goes on, decreases, and again it goes on, increases. Again it goes on, decreases, increases. That means intensity goes on, decreases, and finally it reaches to 0. But in the case of interference, in the case of this is due to the diffraction of Swapna diffraction. But in the case of interference, you will get intensity distribution as like this. That means in the case of interference, you will get same light of same wavelength. That means intensity is same at all the points. That means it consists of interference pattern consists of equally spaced bands, but this diffraction pattern consists of unequally spaced bands. Okay, so here the central fringe is bright. Okay, here the dark fringes are in the interference. Dark fringes are perfectly dark, but in diffraction, dark fringes are not perfectly dark. Okay, because the intensity is not constant, it goes on, decreases. Okay, based on this, we write the difference between the interference and diffraction. This interference and diffraction are similar phenomena. Both are similar phenomena, so this is very difficult to distinguish between this interference and diffraction. Both are obtained by the superposition of waves. Okay, but this interference is obtained due to the two coherent sources, but diffraction is obtained by the single source. Okay. Now we shall look at first difference. Interference. What is interference? It is the interference is obtained by the superposition. Obtained by the superposition of two waves. Superposition of two waves originating from two coherent sources. So this diffraction is also obtained by the superposition, but it is obtained by the superposition of secondary wavelets. It is obtained by the superposition of two wavefront. Okay, the wavefront is coming from two different sources, but here the diffraction is obtained by the superposition of secondary wavelets originating from different points of same wavefront. Okay, that means interference is obtained by two wavefront. Diffraction is obtained by the secondary wavelets originating of secondary wavelets from the same wavefront. The next difference is all the maximas are of same intensity. All the maximum means in maximum intensity point. All the maximum are of varying intensity. All the maximum are of varying intensity. Because in diffraction, the intensity goes on decreases like this. Okay. Third difference is in interference, dark fringes are almost perfectly dark. These dark fringes are obtained by the destructive interference. So dark fringes are almost perfectly dark. In diffraction, the dark fringes are not perfectly dark. Dark fringes are not perfectly dark. Okay. Next difference is the fringe width is the width of the fringes are equal. The width of the fringes are equal. The width of the secondary band, the width of the maximum, the width of the central maximum is double than the width of other maximum. The width of the central maximum is double than the other maximas. Okay. In the interference, bands are equally spaced. We know that in interference we will get alternative bright and dark fringes like this. The bands are alternative bright and dark fringes like this. So bands are equally spaced. In interference, bands are equally spaced. And large in number. They are large in number. Okay. In diffraction, bands are unequally spaced. They are not equally spaced. They are unequally spaced. Unequally spaced and few in number. In interference, bands are large in number. In the diffraction, bands are few in number, because intensity goes on, decreases and reaches shortly minimum point. Okay, and sixth difference is intensity distribution curve. This is the sixth disturbance. This difference. So this is the intensity distribution curve for intensity, and this is the intensity distribution curve for this is the intensity distribution curve for diffraction, and this is the intensity distribution curve for interference. This is the sixth difference. Okay, just to write the intensity distribution curve. Okay, so this completes diffraction. We are going to solve some numericals. First, we have to list some formulas related to this chapter. Okay, starting from Huygens principle, that is, according to Huygens principle, derives the Snell's law, that is ratio of sine of angle of incidence to the sine of angle of refraction is equal to refractive index, that is n21 is equal to sine I by sine R. Okay, and next formula is, so refractive index n is equal to lambda 1 by lambda 2, that can also be written as v1 by v2. That means, where n is the refractive index, lambda 1 and lambda 2 are the wavelengths of the light in first medium and second medium, and v1 and v2 are the velocity of light in the first medium and second medium. And third one is I is equal to R, that means angle of incidence is equal to angle of reflection. Okay, next one is resultant displacement of the wave, that is from interference pattern, y is equal to R sine of omega t plus phi. Here R is the resultant amplitude, omega is the angular frequency, t is the time, and phi is the phase difference. Okay. Next, condition for constructive interference. Condition for constructive interference. There are two conditions for constructive interference. That is, one is path difference, another one is phase difference. So, first one is phase difference. Phi is equal to 2n pi. Phase difference phi is equal to 2n pi, and path difference for constructive interference is n lambda. Here pi is the phase difference, n is the integer, and pi is the 3.14. So phase path difference is equal to n lambda, where n is the integer and lambda is the wavelength of the light. Again, we have to write condition for destructive interference. Destructive interference is found when turf of one wave falls on the turf of another wave, or turf of one wave falls on the turf of crest of another wave. For this, there is also two conditions. That is, one is for phase difference, another one is for path difference. So for phase difference, we have to write pi is equal to 2n plus 1 into pi. And for path difference, we have to write PD is equal to, that is, path difference is equal to 2n plus 1 into lambda by 2. Next, path difference is in the case of interference, that is, path difference is equal to H by D. Okay, here x is the distance between the point O, that means central bright maxima, to P. Distance between the point O to P. With the distance between point O and P. Okay. Small d is the distance between slits. And capital D is the, don't confuse this capital D with small d. Small d is the distance between slits, capital D is the distance between source and screen. Sorry, source, screen and slit. Screen and slits. Okay, this is the formula for path difference. So for nth bright fringe, have to write xn is equal to n lambda d by d. For nth bright fringe, have to write xn is equal to n lambda d by d. Here n is the integer, lambda is the wavelength, d is the distance between screen and source slit, small d is the distance between slits. For first bright fringe, n becomes 1, that is x1 is equal to lambda d by 2. For second bright fringe, n is equal to 2, so x2 is equal to 2 lambda d by 3. And for third bright fringe, n equals 3, that is x3 is equal to 3 lambda d by d, and so on. Okay. Next, fringe width, that means width between any two consecutive clusters, or any two consecutive bright fringes, or any two consecutive dark fringes is known as fringe width. That is given by beta is equal to lambda d by d. Here also d is lambda is the wavelength, d is the distance between screen and slit, and small d is the distance between the slits. Okay. Next, for diffraction pattern, path difference is equal to a sin theta. Path difference is equal to a sin theta. Here a is the distance between slits. In the first, we have to use d for the distance between slits, but for diffraction we have to use a for distance between slits, between two slits. Okay. And capital D is the distance between, theta is the angle of diffraction. Theta is the angle of diffraction. Okay. Next, for diffraction maximum, for diffraction minimum, we have to write path difference, or a sin theta n is equal to n lambda. A sin theta n is equal to n lambda, where a is the distance between the two slits, theta n is the diffraction angle for n fringe, and n is the integer, lambda is the wavelength. Next, for diffraction maximum, have to write a sin theta n is equal to n plus half into lambda, where n is the integer, lambda is the wavelength, lambda is the angle of diffraction, and a is the slit width between two slits. Okay. 13. That is width of central maximum. On either side of the width of central maximum, on either side of the minima, either side of first minima, or on one side of the first minima. We know that this is the diffraction intensity distribution curve. In diffraction, intensity goes on decreases like this. So this is the central bright maximum. Okay. So the distance, this is the first minima, and this is also first minima. The distance between the central maxima and one first minima, is given by lambda d by d. Okay. So lambda is the wavelength, d is the distance between source and screen and slit, and d is the small d is the distance between two slits. Next, width of central maxima on this distance. This distance is also same. That is lambda d by d. Then what is the total distance of the central maxima? So the total distance of total width of the central maxima is lambda, width of the central maxima from one side plus width of the central maxima on other side of the first minima. So total width of central maxima is equal to 2 lambda d by d. Okay, so these are the some formulas which are very important to solve the problems or numericals. Okay.